So you may remember at the end of last class, we talked about what was called the common logarithm. We said that if you see a logarithm, and it says log, and there's no base written, we're going to say it has an implied base of 10. So we argued that, and so the nice thing is your calculator has the common logarithm built into it. If you're on a TI-84, and I don't have mine right here, so I'm going to look up a picture of it, and I can tell you exactly where the common logarithm is. On there, it's going to be on the far left-hand side, just next to the 7. You should see the log button. Now, yours may or may not let you choose a base. If it doesn't let you choose a base, it's implied to be a base of 10. So if you just go in there and you do log of 1,000, again, no base written. Well, you're asking 10, the implied base, to what power gives you 1,000? So that should give you a 3. So everyone go ahead and do log of 1,000, close off the parentheses, and hit enter. And is everyone getting 3? I would think so. So it turns out we now have a calculator that can evaluate logarithms for us, which is really nice. I mean, you can do logarithms of kind of exotic things, logarithms that don't fit into a basic mold, and ones that you just cannot do off the top of your head. It's just not going to happen in this lifetime. And so the log of 87, you should be getting like 1.939. I'll just copy paste it. Should be getting something like that. So there's the common logarithm, but actually a lot more importantly and a lot more useful is the natural logarithm. This is going to be a logarithm that has an implied base of e, and we don't write the word log anymore for it. We use ln. You might literally say ln x, or the natural log of x. Something like that. And again, this is going to be a logarithm with a base of e. On your TI-84 calculator, you should see the ln button just below the log button, which is quite apt. So the logarithm buttons are right next to each other. Now you might wonder, why would we ever care about e? Remember, e is a constant in mathematics, kind of like how pi is a constant. Pi is like 3.14159. E is roughly 2.71828. And just like pi, excuse me, just like pi, it goes on forever and ever. and it does not repeat a pattern. It's an irrational number.
Good morning. The National Honor Society is having a meeting at this time in room 111. National Honor Society, your meeting is going on now in room 111. Thank you.
National Honor Society, very nice. But anyways, so this is roughly what E is. Why in the world do we care about E? I mean, pi, we can understand why pi is useful because pi is the ratio of a circle's circumference to its diameter. We can also calculate the area of a circle, and we need to use pi in order to do that. So we immediately can see why pi is important. Why in the world is E important? Well, it turns out E is a very famous, super important constant in mathematics. It was discovered by one of the most important mathematicians of all time named Leonhard Euler, or at least he was one of the ones to really formalize it. And what it does is it can tell you, it's a convergent state for an exponent for like a compound interest formula or something that grows or changes over time. And it turns out it's just the most efficient base to use in an exponential equation for a couple of reasons. Again, we don't quite get into the heavy lifting reasons, but E is very important constant in mathematics, to say the least. And so you can do, well, you can do all kinds of things. You can take the natural log of 4. You can pop that into your calculator, close off the parentheses, hit enter. Let's see, I'll do it right now, and I get about this number. And again, it looks like, oh, well, it goes out to this many decimal points, but then it stops. No. Most natural logs of regular old numbers are going to be irrational and go on forever and ever. You can also do the natural log of E itself. You can find E on your calculator in a couple of places. If you hit the second button near the top left, and then you hit the what it looks like is the division button. Yeah. It won't actually divide because you hit second, which is like a shifting button. It will bring up E. And so you can do the ln of E. Of course, that's just going to give you 1 because the ln has a base of E, and you're saying E to the first equals E. So the natural log of E is 1. So lots of interesting implications about E. Let's use the calculator to compute a few extra interesting ideas. So evaluate using a calculator. How about the natural log of E to the 2/3 power? Oh my goodness, let's get my 3's there. There we go. Well, actually, it turns out this is one we can do without using a calculator, though you can. But think about it. Even though the base isn't written, it's the same as a logarithm with a base of E. You're basically asking with this logarithm, E to what power gives me E to the 2/3 power? Well, obviously, that's got to be 2/3.
Alex Nagerson, please come to the office. Alex Nagerson.
So if you put into your calculator the natural log of E to the 2/3 power, and you make sure to get your 2/3 fully in the exponent, then you go over to the right and close off the parentheses and hit enter. It should give you 2/3. Now, it may not give it to you as a fraction. It may give it to you as the decimal point 6666, and at some point it's going to put a 7 at the end because the calculator is going to round for you. But that is what's going on here. So technically we could have done that one without a calculator. The natural log of 1 over e to the 6th power. Well, this is still a logarithm with a base of e. Notice I have 1 over e to the 6th. I can actually, if I really wanted to, I can rewrite this as I can bring the e to the top, but I have to make that a negative power on the 6. So we can get the natural log of e to the negative 6th. And so just like the last one, it's pretty straightforward. I'm asking the logarithm with a base of e. I'm saying e to what power gives me e to the negative 6th power? Oh, the answer's got to be negative 6. Of course, you can use your calculator to do that, but it's much better to just reason through it. If you can notice some patterns and see things, it is. Now let's have a brief discussion about the calculator. First of all, just if you're not super familiar with the calculator you're using, if you want to put a negative number in, you cannot use the subtraction symbol that's right there where the plus, minus, times, and division symbols are. You can't use that subtraction symbol because that actually wants to literally do the operation of subtraction. You need to separately use a button that is specifically reserved for taking the negative. And that one's going to be near the bottom of the calculator, next to the decimal point, and just down and to the left of the enter key. That's going to be your negative button that you use for negative numbers. So just keep that in mind. Make sure if you are putting this in the calculator, you do E and then you do caret and you do all of negative 6. Let's have a very brief discussion about the calculator. Let's have a brief discussion of the calculator. You want to use the calculator so badly. It is just in your nature to say, ooh, just give me that calculator and I can do great things. Put me in, coach. And I understand that it is very seductive to want to use that calculator. And there are times when you simply have to use the calculator, or you could do a computation without it, but it would take you 5 minutes instead of just quickly punching the buttons in. So there definitely is a time and a place to use the calculator, and we have reached that time in this class. However, in general, if you can reason through something without using a calculator, you are setting yourself up for so much better things in your future. You may think that being able to get good grades and do well in school is the most important thing in the world. And to some degree, it is very important and is something that you should really pay close attention to. But sometimes you can trick yourself into thinking you have a lot more knowledge than you really do. And over-relying on the calculator is one of those ways you can trick yourself. We're getting to a point in the world where it's so much better to just be naturally able to understand mathematics without the use of a calculator, especially because the higher you go up the mathematics tree, the less math becomes about just straight computations. Math, as you get into its more pure forms, is actually a philosophy, and is something that is meant to be thought about very heavily and reasoned through. And currently, it's not something a calculator can do, because the calculator is just about crunching numbers, mostly, for the most part. We also, in the world we live in today, we need an ever-expanding skill set in order to, frankly, be competitive enough to get into certain jobs. That is just clearly where the trends are going with certain types of jobs and positions. Those jobs and those positions want people who are naturally very good thinkers or are trained very good thinkers. Those who can look at a problem, who can think of multiple ways to solve it, maybe even rule out some of those ways, all in their mind, all by just sitting down and thinking about it and reasoning through it. So you may hate not being able to use a calculator, but it is actually training you, it's training your mind to think about things as clearly as possible. So I would warn against using the calculator. The calculator is great for certain things. It's impossible to do certain processes without the calculator. But how much of yourself are you letting go? How much of your own ability to learn and reason are you letting slip through the cracks by using a calculator? Anyways, as I say that, now let's do a quick problem that does require the calculator. Because look, I can tell you the natural log and then e is involved here and a logarithm has a base of e. So maybe there's some trickery I can do. But the natural log of 39, good night. I can't do that I don't really have any cute methods for doing that. And there's no reason to. So in this particular case, yes, we do need to use the calculator. So you can literally, in your calculator, you can go to the TI-84, you can clear out and create a new line, and you can do ln, it'll open a parentheses for you, do 39, close that parentheses. You can then do plus, and then you can start a new ln of 998, close off that parentheses and hit enter. And this calculator will do all that for you. That's wonderful. But just keep in mind that in the long run, you're not doing yourself a whole lot of favors if you only know how to do math on a calculator. Turns out you don't actually know how to do math if you can only do it on a calculator, because that's not what mathematics is. And so if you do that, you can see it's whatever that is, and it's going to go on forever and ever. It's just that your calculator has to stop at some point. It's only going to show you so many digits of something, because calculators are mortal. They're mortal tools. So as I say this, now you're in the calculator and you're like, okay, this calculator, the TI-84, only comes equipped with 2 logarithmic bases, a 10, the common log, or e, the natural log. But Josh, I want to experience the whole wide world of logarithms. I want my calculator to be able to take a logarithm with a base of 17.5 or a logarithm with a base of 2. You want all kinds of different logarithms out there, and I can feel you on that. I understand that completely. Now, some of the newer TI-84 models, whenever you hit the log button, it might actually let you put the base of the logarithm in there. Ooh, that's fancy. If it doesn't, though, we actually have something called the change of base formula. And what the change of base formula is it is a formula that lets you compute any logarithm with any base. The change of base formula if you want to evaluate a logarithm with a base of a and then an argument of x. So remember, this logarithm is saying a to what power gives you x. You can actually write that as the ratio of 2 separate logarithms. Log base c of x. This is going to be c divided by the log base c of a. And this doesn't look all that powerful, but we're going to see that C is any valid logarithm base. And I mean any. So suddenly we can break this single logarithm into two separate logarithms. Why would we want to do that? Doesn't that make it more complicated? Actually, it gives us a tool for evaluating any logarithm we want with any base in the calculator by switching over, separating it into two logarithms that can have any base we choose, any base we want on planet Earth. We can use a base of 5 here. We can use a base of 17 here for C. Or the fact is, our calculator only has two bases that you can use, 10 or the constant E. So actually, when we do this, we should be using the common logarithm or the natural logarithm. So let's use the calculator to evaluate some of the following logarithms. How about the log base 3 of 7? In other words, 3 to what power gives me 7? Now, normally, if I'm in the calculator, what am I supposed to do? What am I supposed to do? I'm in a calculator and I don't have a logarithm that has a base of 3. Well, okay, I have a solution for you. Use a log with a base of 10. Use the change of base formula, and you're going to use log base 10 of 7 divided by log base 10 of 3. And then remembering that the log button on your calculator is the common log, it automatically has a base of 10. You don't even have to put the 10. Oops. It's just, you can do log of 7 divided by log of 3. Now your calculator will put parentheses around that. Make sure you close off the parenthesis on the 7 before you hit the division key. And now try punching that into your calculator. I'll punch it into mine, so we can make sure we're on the same page. And you should be getting this number. $1.771243 blah blah blah. And again, we won't decide what to round to. If you're on your homework might say, oh, round to 2 decimal places. Okay, 1.77. So it just depends on what you're working on. What's cool is I stand by what I said, where when we use this change of base formula, you can use any base you want, any logarithm base. That means I could use a log with a base of 10, or I could use a log with a base of E. I can do the natural log of 7 divided by the natural log of 3. So try that out. Go into your calculator, do ln of 7, make sure to close off the parentheses, then do divided by the ln of 3, close off that parentheses, and hit enter. And you should get this exact same value we had. So just some pretty interesting implications here for this change of base formula. Pretty interesting. All right, let's work one more example together. Let's say, given that f of x is equal to e to the x power, where e is that special constant, x is your variable, and then g of x is equal to the natural log of x, ln x, let's find some interesting values here. Let's start with f of the natural log of 4. Oh, wait a minute. Don't lose sight of the forest from the trees. If you're plugging numbers into functions, then you're doing function evaluation, which is exactly what this is. The natural log of 4, well, I can't tell you what that is off the top of my head. I can tell you it's really not so bad. It's some number. So let's see. Let's try it out. F of ln of 4. So wait a minute. Here's my f function, e to the x. So I want to plug ln 4 in for the x, and it's going to be e to the natural log of 4. Yeah, that's exactly right. We're going to take e and raise it to the natural log of 4. Now, I happen to have a little bit of kind of magic or witchcraft, not literally, but I happen to have a little bit of skill here. And I know this actually is going to come out to exactly 4. Which looks a little bit wild. Excuse me. Which looks a little bit weird. You might think, well, is that just saying that the E and the LN are canceling out? Actually, that's kind of true. E, as long as you're raising it to a power that has the LN here, then they kind of do cancel out and you're just left with this 4 here. If it was E times the ln of 4, no dice. But you have to do E raised to the ln of 4 power. Suddenly they kind of cancel out, leaving you with just the 4. But wait a minute, there's actually good reason for that. Let's zoom way in here. Think about what ln of 4 is asking. This is asking e to what power gives me 4. That's what it means whenever it says, what's the ln of 4? Because ln is a logarithm with a base of e, so I'm saying, so perhaps this might help you to see it. You're saying the log base e of 4, that's saying e to what power, question mark, gives me a 4. So whatever ln of 4 is that exponent. It comes out to being that exponent. And then I'm doing e raised to that exponent. So of course it's going to give me a 4 here. It's almost just like you're deconstructing the entire purpose of logarithms, or their entire existence here. So ln of 4 answers the question, e to what power gives me 4? And then I'm actually raising e to whatever that power is. I'm doing e raised to whatever that power is, which is expressed by the natural log of 4. So of course it's going to give you 4. Awesome. So I didn't even need to use a calculator there. Can you use a calculator? Yes, you can. You can find your E button. You can use the caret key for exponents. I would open up a parentheses. Then I would do ln. It'll open up another parentheses of 4. Then you close off 2 parentheses. In other words, in the calculator, do e caret, open a parenthesis, ln, it'll open a parenthesis, do 4, hit 2 parentheses, and then hit enter, and you'll get a 4 for that. So useful stuff, useful stuff. Let's look at another one, and these are kind of the mind benders. F of the natural log of 1 over e to the 7th power. Okay, so the natural log of 1 over e to the 7th, but I'm plugging that into the function e to the x. So it's going to be e raised to the natural log of 1 over e to the 7th. Yeah, that's exactly right. Put this thing here into the function for x. Now you could plug this one into the calculator. It's not going to do a whole lot to help you. You can get a decimal form, but if you wanted an exact form, you can recall that the e and then raising it to an ln, they kind of cancel each other out in a way, and all you're left with is this argument of the logarithm, 1 over e to the 7th, which can further be expressed as e to the negative 7th power, which will be a pretty darn small number between 0 and 1. So don't get tricked into thinking that the calculator is going to save your life here in every single problem. Do not trick yourself into thinking, oh, I don't have to study for the next exam because I have a calculator. That would be disastrous. Let me just tell you that. Because there's still concepts you have to come in fully understanding. You can't just walk in with nothing. You got to walk in with a lot. So do not get so easily seduced by your calculator. It is the path to the dark side. Let's try out a couple more. How about g of e cubed? Well, don't lose sight of the forest for the trees. This is just saying take the function g of x and plug an e cubed in everywhere you see x. Okay. So let's see, that's going to be just the natural log of e cubed. Now, I suppose that we can just plug it into the calculator. Okay, that's not going to be how I do it. Let's think through it reasonably. Let's think rationally here. The first thing you might notice is now the tables are turned. Earlier, I was doing e and raising it to a natural log of something. And the e and the natural log kind of canceled out, and all I was left with was the argument of the logarithm. But now I'm flipping the tables. Now I'm taking the natural log of e raised to some power. And so it turns out, once again, the natural log and the e are going to cancel each other out. It's like when you're taking a square root and then squaring something. Or if you choose to square something first and then take the square root. Just because you flip the order of doing the operations, they still cancel each other out. It's just like if you add 5 and then subtract 5. Or if you flip it around and subtract 5 first, then add 5, ultimately they undo each other. So it's like the ln and the e kind of undo each other's effects, and we get 3, this thing here. That's exactly what's happening here. Another better way to see it is, remember, the ln is a log with a base of e. So if you want to write it in logarithm terms and see what the base is, this here can be rewritten as log base e of e cubed. And now remember, think about what a logarithm is doing. You're saying e to what power gives me e to the third power? Well, obviously it's got to be 3. 3 has to be the power so that you get e cubed. If you still don't see it, rewrite as an exponential. Remember? Let's say we don't know what that power is. Let's just call it x. So I'm going to rewrite this thing as an exponential. It's e to the unknown power gives me e cubed. And now you can immediately see, oh, well, clearly x would have to be 3 for this to be a true statement. So you get e to the third and e to the third. And thus, 3 is our solution. Again, that's somewhat useful for doing quick computations without even needing a calculator, especially because I can deceive you. I can lull you into a false sense of security with the calculator, and then I can give you problems that the calculator will not give you a whole lot of guidance on. So be careful. The calculator is not the end-all, be-all. And I keep preaching about that, and it's because mathematics has nothing to do with calculators at the end of the day. The calculator cannot do the math for you. You got to do the math. Finally, let's compute g of e to the ln of 2. Which is pretty wild. Well, we plug e to the ln of 2 into the g function, so then it's going to be like that movie Inception, something wrapped inside something, wrapped inside something. There's a couple of ways to do this one, and notice I'm not going to use the calculator one bit, especially because the answer to this, if you were to just plug this into the calculator, it'll give you a nasty decimal number, and you won't know what its exact form is. But anyways, in this case, look at the pattern from the last one. We did a natural log of e raised to a power, and the answer was that power. Same thing going on here. We're doing the natural log of e raised to a power. That power is ln2, so the answer will be ln2, which will be some number. You can put it into the calculator if you wanted a decimal form of it, but ln2 is sufficient for me. That one makes me a happy boy. So this little experiment gives us a few potentially useful facts. We will generalize them to any log base. If you have any logarithmic base and you raise it to a power where the logarithm has the same base, it's kind of like these cross out, and you're just left with x here. In spirit, we don't cross them out, but in truth, that's very similar to what's happening. That's just why e to the ln of 4 was just 4. This is e, we're raising it to a logarithm with a base of e. They cancel each other out, and you're just left with 4. But that's actually going to be true of any valid base. I could do 2 raised to the log base 2 of x, it would just give me x. Our other little fact is the log base b of b to the x is just equal to x. In fact, this was a logarithmic tool we learned earlier. It's kind of like we're flipping the order of operations here. So all of that wraps up section 4 of this chapter 4. We're going to look at one more section in chapter 4. This will be section 4.5. And now we're going to get into the meat and potatoes of it. We're going to get into the meat and potatoes of it. We're going to look at exponential and logarithmic equations in solving them. Here's what we can do. You're going to be given some equations that have exponents and logarithms in them. The variable may not be where you want it, so you can't solve these using older methods. For instance, your variable, look at this one. You have x times the log of 5, which is automatically a log base 10, equals 7. Technically, yeah, that's technically a logarithmic equation. You see there's a logarithm going down there, but it's not exactly a difficult one because x is just being multiplied. I'm not doing x raised to the power of log 5. I'm doing x times log 5. So I didn't need to know a whole lot about logarithms to know I just need to divide both sides by log of 5. And then I can just go pop that into a calculator if I wanted to get a decimal approximation for that answer. So you may see that one that's that simple kind of pop up, but that's not really going to be in the spirit of what we're going to do to solve some of these equations. These equations are just going to be a little bit more complicated than that. Some new methods we will use. We can take the logarithm of both sides of your equation. That's one thing we can do, and that is a protected thing. It's just like you can add 7 to both sides of an equation. If that helps you, you can divide both sides of an equation by a number. If that helps you, if that's the tool you need to use to solve that equation, have at it. You can also take a logarithm of both sides of the equation under certain conditions that we're not going to get into detail about. What base should you use? Whatever makes sense. Because if you're taking the logarithm of both sides, your logarithm has to have a base. It's by definition. What base should it be? Well, you're just going to have to kind of feel it out and look at the problem you have. And if you see a base floating around, you're probably going to take the logarithm with the same base. You can also do something really funky. And it's hard to write this one out. You can express both sides as the exponent of a base. That one's just kind of hard to write out. You'll have to kind of see it in action. Basically, I can take both sides of my equation and then turn them into the exponent of some number. So for example, let's say I have x equals 5. What I could do, I can say that x and 5 are both the exponents of some other number. And suddenly I've thrown them into the exponent of something, and I have to use the same number on both sides. In this case, I used 7 because I just picked a number out of nowhere, a number out of my head. Why on God's green earth would we want to do that? Doesn't that make this equation more complicated? Yes, this equation, but we're going to run into situations where you're going to have equations, and actually we're going to use the fact, especially if there's logarithms involved, we're going to use the fact that you can sometimes cross out a logarithm. So while doing this may not have been super helpful on this problem, what if my original problem had actually been log base 7 of x equals 5? Suddenly, that makes everything a lot more interesting. Because now this would cancel out, and I'd just be left with x equals 7 to the 5th. And suddenly that became a very useful way of isolating my variable. And then 7 to the 5th will be a pretty large number, but the calculator can calculate 7 to the 5th. So these are going to be our new tools. You can either take the logarithm of both sides of the equation. If that helps you, go for it. How do you know it's going to help you? Well, experience. We're going to work a bunch of equations today. We're going to solve a bunch of equations. Or you can do this little trick. So, 2 new wonderful tools that we can use. So let's try some of these out. Let's solve some of the following. How about a simple one? 2 raised to the x power equals 10. Two raised to the x to the power equals 10. So what I'm trying to find, what I'm ultimately trying to do is I'm trying to say 2 to what power gives me 10? What do I have to raise 2 by in order to get 10? The answer is not 5, because that would say 2 to the 5th, which is 2 times 2 times 2 times 2 times 2, which is 32. We're not multiplying, we're taking an exponent. It's going to be kind of an ugly number. So 2 to what power gives me 10? Well, we can try a couple of strategies. We can take a logarithm of both sides. Another strategy I didn't express that I probably should have is that you can rewrite as a logarithmic equation. 2 to what power gives me 10? Oh, that sounds like I'm just asking log base 2 of 10 equals x. And yeah, that's exactly what I'm asking. Now what I'll do is I'll put the x on the left-hand side of the equation. And so now I just need to evaluate the log base 2 of 10. I can use my calculator and the change of base formula. I'll use natural logs. ln of 10 divided by ln of 2. And we can pop that into a calculator, use parentheses appropriately. So we can do natural log of 10 divided by natural log of 2. And so remember, I use change of base formula. That's how I made the leap from here to here. I can use any log base I want, so I use log base E because my calculator comes equipped with an ln tool. So I go back to the calculator, I do ln of 10 divided by ln of 2, and I'm going to get this number. It'd be like, that 3 point whatever. And that number is going to go on forever and ever and ever and never stop, most likely. We can probably prove that that's going to be irrational. And that's the answer. So it may ask you to round. It might say round to 3 decimal places. Okay, so it'd be 3.322. Let's try another one out. Point 0.7 raised to the 3x power equals 8. So once again, my variable is up here in the exponent. Here's what you could do. You could rewrite as a logarithm or a logarithmic equation. That's fine. Or you can take the logarithm of both sides. And I can use whatever base I want. Let's try this second strategy because we just did one with the first strategy. Let's try this one out. What base should we use? Well, you might want to use a base of 0.7 on your logarithm. Yeah, but I know I'm likely going to end up punching buttons into a calculator. So I'd rather use a base that the calculator knows. And that's going to have to be base E or base 10. So I'll use base E. Let's take the ln of both sides, the natural log. So I'm going to take the ln of this side. I'm going to take the ln of this side. And so I'm going to end up with this. Just kind of going to rewrite it here. Now you might say, Josh, how does this help me? What does this do for me that's going to make my life any bit easier? Ah, this is where we need to remember some of our logarithm rules, some of our logarithmic manipulations we can do. Remember last class we talked about the product rule for logarithms, the quotient rule for logarithms. There's also the power rule for logarithms. And the power rule is going to allow me to take this exponent here and bring it down, and suddenly my variable is no longer in an exponent. My variable is back on level playing field. And so now I've got my x here. I need to isolate x. I need to divide both sides by this 3. I also need to divide both sides by the ln of 0.7. And that will get x completely by itself. And actually, since I'm doing both 3 I'm dividing by and also 0.7, you could multiply them on bottom. Some of the students have observed that the homework switches around on the number of decimal places it requires in the answer, 3 or 4. Is the test also going to switch between them? Yes, it very well could. So just pay very close attention, read the problems carefully. Of course, remember I collect your scratch work, and so if you get a problem wrong on the test, but it's only because you rounded incorrectly, but otherwise you did everything else right, you're going to get basically full credit on that problem given back to you. So yeah, read it carefully, make sure to round to the right number of decimal places. But remember, I'm going to review the exams, and if I see you had the right answer in spirit, I'm not really going to take off for rounding error. So short answer, yes. Long answer, yes, with a but, where the but is good for you. So now we need to do the natural log of 8 divided by 3 times the natural log of 0.7. Some wisdom I would give you is to put this entire denominator in parentheses when you input it into the calculator. That way it'll know to do the 3 and the natural log of 7 all as the denominator here. And so I'll compute it with you just so you can compare, make sure you get the same thing. And you'll get a negative number. That's okay. Remember, these might come out negative. You just can't use a negative base. And the number I am getting is negative 1.94. So if I want you to round to 3 decimal points, negative 1.943. And so this section of solving these exponential and logarithmic equations is just kind of us working out in the wild here. We're facing some interesting problems, some interesting equations that we need to solve. So we need to ramp up our techniques for solving them. Here's another one that looks interesting. 4 raised to the x minus 4 power is equal to 3 to the 2x power. So 4 to the x minus 4 power is equal to 3 to the 2x power. Boy, howdy, looking at this, just at the get-go, you're like, how in the world do I solve something like this? The first observation we'll make is over here, my variable is in the exponent. Over here, my variable is in the exponent. I'd like that to not be the case. I'd like to not have to do that, have my variable up there. The way I can handle that is if I choose to take a logarithm of both sides, I can use that power rule for logarithms. That's going to allow me to bring this exponent down, and suddenly it's no longer in an exponent. That's exactly why the power rule is super useful for logarithms. So let's take, now I'm going to take the logarithm of both sides. What logarithm should I use? Well, here I have an exponent of base of 4. Here I have an exponent base of 3. So do I choose 3 or 4? Well, no, let's choose something that our calculator already has built into it. So let's take the natural log of both sides. So you're going to end up with the natural log of 4 to the x minus 4 power equals the natural log of 3 to the 2x power. So we're going to bring down the power using the power rule for logarithms. That's the whole reason we took a logarithm on both sides. And now we might have to get a little bit crafty with how we solve this one. This one may not be pretty. So we're going to have to really use our algebra rules here. So the x minus 4 gets brought down, but I want to note that I need to kind of put the x minus 4 in parentheses, so I know this whole thing is being multiplied to the natural log of 4. And then on the right-hand side, I'm going to get 2x times the natural log of 3. Now this is where things are going to get a little bit wild. We need to isolate the x. The problem is there's an x on both sides. Another hiccup, another problem, is that in each case, the x is going to end up getting multiplied to a natural log. So it's just not going to end up looking super pretty when we get down into the details of solving it. Now, remember a few things. The natural log of 3, I don't know what it is off the top of my head, but I know it's just a number. It's just a constant number. Over here, the natural log of 4, again, I don't know what it is off the top of my head, but I know it's just some number. It's just some constant number. So what I'm going to have to do is I'm actually going to have to start by distributing this out. This natural log of 4 out. And we will have to adjust some of our space here because there's a lot of meat left on this bone. But I'm going to end up with basically x times the natural log of 4 minus 4 times the natural log of 4 equals, and the right-hand side did not change or anything. Now, because I'm going to run out of space, I'm going to have to bring this one up to the top. So I distributed out that natural log of 4. Now I want the x to be by itself, ideally on the left-hand side. This does not have an x in it, so I'm going to jump it over to the other side. So we'll do plus 4 natural log of 4. And just so I don't skip too many steps or anything, now let's write what I have. Now, what I want to do is I want to get all my x's to be on the left-hand side. I want all my x's on the left-hand side. So now I'm going to have to subtract over this thing. So I'm going to end up with this. Now it's hard to see what to do here. I've got x times natural log of 4 minus 2 times x times natural log of 3. But what I'm going to want to do is I'm going to want to factor out an x. I'm going to have x. I'm going to factor it out of here. So what's going to be left is ln of 4 minus, then I've factored an x out of here. So what's left is 2 times natural log of 3. So once again, I'm going to have to clear everything up here and bring it back to the top. That is one of the unfortunate limitations of using this limited whiteboard. But now I've got x almost isolated. It's being multiplied by this whole thing. Remember, this is just some number. Whatever ln of 4 is, then I'm subtracting 2 natural log of 3. That's just some number. That's just some number. So I'm going to divide both sides by that number. By ln of 4 minus 2 ln of 3. Divide this side by ln of 4 minus 2 natural log of 3. And you're going to get something a little bit ugly. Oof. Take a moment, breathe a little bit, because we just solved a pretty nasty equation. This is all going to just be some number. 4 times the natural log of 4 is some number. ln of 4 minus 2 ln of 3 is some number. Then it's just some number divided by some number. So we can use the calculator to compute this. If you're on the TI-84, I would use this. I would type it in exactly like this. Use the LN tool. There's the division sign here. Notice that I put the whole denominator in parentheses. I put parentheses around ln4 minus 2ln3 because that's exactly what we want it to look like. And now I'll go use my calculator for this. Well, never mind, it won't let me copy paste, so I'll just do it myself. And you should end up with, it'll be an ugly number. Negative 6.838, blah, blah, blah. We'll round it to the nearest thousandth, which is 3 decimal places. All right, that's it for today.